Hello, everybody. Welcome to the last Science Academy meeting. Let me go back to Turkish. Herkese selamlar tekrar. Haziran'ın son gününde, kısıtlamaların son bulduğu bu günde Bilim Akademisi'nin son sunumunu yapıyoruz. Çok değerli bir araştırmacı bizle birlikte. Bu çok değerli araştırmacıyı Oxford'dan Profesör Chris Smith'i Bilim Akademisi'nin kurucu başkanı ve 10 yıldır Bilim Akademisi'ni çok güzel bir yere getirmiş olan Ali Alpar hocamız tanıtacak. Ben sözü Ali hocaya bırakacağım. O anlatacak size. Sonra konuşmayı dinleyeceğiz. Ali hocam, söz sizde.
Çok teşekkürler Pınar hocam. Thank you very much. It is my great pleasure to have with us this evening Professor Sir Chris Llewellyn Smith. In addition to his contributions as a particle physicist, Chris Llewellyn Smith is a leader in science administration and science diplomacy. He was Director General of CERN in the period 1994 to 98, at the time when the Large Hadron Collider was approved and the construction was started. As president of the Sesame Council, now Sesame is the acronym for Synchrotron Light for Experimental Science and Applications in the Middle East. Chris was president of the Sesame Council from 2008 to 2016, and in his ongoing support of Sesame, he has been crucial in bringing together scientists, young and old, from Turkey and from Israel and Palestine and Iran and other countries of the Middle East. This is no small feat, as you can imagine, in science diplomacy, and indeed for diplomacy through science. Chris has more recently worked on energy issues and served on many advisory bodies, nationally and internationally, in these decades of global warming, worries about sustainable energy supply, and all of these big issues being darkened by post-truth and alternative facts all over the world, not least in this country. So the considered reasoning of science is the only key to solutions for our complicated problems. This talk was originally conceived as a Science Academy conference on the Boğaziçi University campus. First the pandemic, and then the current siege on Boğaziçi University has led us to organize this as a Science Academy webinar for all science enthusiasts and the public interested in realistic trials and scientific solutions for sustainable energy. So I'd like to welcome everybody, and I turn the screen sharing over to Professor Llewellyn Smith. If you have questions, please just note them. They will be grouped and addressed at the end of the talk. Okay, and that's all for me. Welcome again, Chris.
Thank you very much. So let me find my talk. Here we go. Right. So I'm going to discuss whether we can meet future energy needs sustainably. But first I need to say, what do I mean by sustainable? Well, sustainability, I think, means stopping the emissions of carbon dioxide and all other greenhouse gases. It'll be very difficult to actually stop them, probably still be some, But in that case, we're going to have negative emissions, take carbon dioxide out of the atmosphere, because we need to get to what's called net zero. Why should we do this? To prevent dangerous climate change. And I will remind you of some of the evidence for climate change and the effects it can have in a minute. If we do that by stopping burning fossil fuels, there will be a bonus. It'll reduce air pollution, which is causing a very large number of deaths. Why must we actually stop emissions and not just slow down? I'm going to discuss that. It doesn't seem to get discussed much publicly, but it's behind all the policy taken by the International Panel on Climate Change. Then I want to ask, how is the world doing stopping emissions? Not too well. The talk is going to be focused on carbon dioxide emissions produced by energy production. So I'll look at the current role of fossil fuels and expectations for the future, and give a couple of reasons why decarbonisation is very difficult. So having explained that it's necessary, but it's difficult, then most of my talk will be on how we might be able to do it. So I'm sure you've mostly seen pictures, plots showing the air temperature of the world over the last 150 years or whatever, and it's absolutely clear that the temperature of the atmosphere is going up. But in those graphs, the temperature jumps around a bit. It goes up by different amounts in different years. Sometimes it goes down. And the reason for that is that the output of the sun is not constant, actually. It fluctuates a little bit. And at the same time, volcanoes throw things into the atmosphere which blot out the effect of the sun. What happened? But there's no question from the data that the temperature of the atmosphere is going up. So what happens to the extra heat in the atmosphere? It gets transferred to the ocean. But that happens more slowly. So the heat that's going into the ocean today is not just from the emissions, the extra heat that came in the last year, it's the extra heat that's accumulated. So it's much smoother. So if you look at that, this is a plot of the heat content of the ocean, the top 2,000 meters, in the last 60 years. And you can see absolutely clearly, without too much jitter, it's going up. Now, what happened here when the slope changed? That's about the date when the Chinese started to industrialize in a big way and build a lot of coal power stations. Now, there are many effects of climate change, and we see many things that are consistent with climate change. For example, some of you may have read there is a heat wave in the Western United States and Western Canada. The temperature yesterday in Lytton, town a little bit north of Vancouver in Canada, was 49.5 degrees. In that town, the maximum average temperature in June is 16 degrees. It was 49. This is consistent with climate change, but you can't say that's proof of climate change. But there are many things where the evidence is pretty conclusive. For example, the sea level is going up because it's getting hotter, so it's expanding. And we see the effects in forest fires in the Western United States, the numbers going up consistently over several decades, and the period in which they happen is going up. And among the many effects of the temperature which are going up, which will change agriculture, have a lot of effects on human life, there could be some which are really disastrous. For example, if the glaciers in Antarctica and Greenland melted entirely, that would lead to a sea level rise of something like 2 meters. Now, the experts say that's quite unlikely, but still, there's something like a 10% chance that it would happen. 2 meters is a lot. At the same time, it can change the monsoon, affecting the lives of billions of people. The Amazon forest can die back, slowing of the North Atlantic circulation. These are all what are called tipping points, big changes. That would change the temperature in the United Kingdom, where I live, if the Gulf Stream stopped. Disappearance of the Arctic ice. Now, the Arctic ice is floating, so if it disappeared, it wouldn't change the sea level, but the Arctic ice reflects sunlight back into the atmosphere. If it goes, which it quite likely will, that sunlight will mostly be absorbed by water, lead to something like 0.5 degree rise. The permafrost in Siberia and northern Canada could unfreeze, releasing huge amounts of methane. Now, why do we have to go to net zero? Why is it not enough just to slow down? So let's look first of all at global CO2 emissions. It's a bit out of date, this is historical, and this is going to the future with sort of business as usual. Everybody goes on burning fossil fuels until everyone in the world is burning as much as they want, and then fossil fuel burning would stop. So that would be emissions with business as usual. The atmospheric concentration of CO2, when we stopped increasing fossil fuels, wouldn't go down because the CO2 stays in the atmosphere for a very long time. So as long as we're emitting this level, even if it's constant, the CO2 will keep going up, maybe not quite as fast, but it'll keep going up, and the warming will keep going up. So that was what would happen with business as usual. What happens if we stopped emissions? Well, if we stopped emissions, the atmospheric CO2 would go down. It would go down because it would be absorbed by the ocean. And after maybe a few hundred years, it would reach some level like it's still going down at this point, some level like here, and then it will stabilize at a level like this. And then after tens of thousands of years, the CO2 will be taken up by rocks. Now, if the CO2 concentration goes down, that means that the imbalance between energy coming into the earth from the sun and going out will change. On the other hand, right now, there's more energy going in than out, so the temperature will have a tendency to go on rising. And the temperature will have a tendency to go on rising until the excess temperature has all been absorbed by the oceans. So if we stopped emissions, there are two tendencies. One is for the temperature to rise until the extra heat's got to the bottom of the ocean. The other is for the driving force, the rate at which the earth heats, to go down until the CO2 gets to the bottom of the ocean. Those things happen on the same time scale, and the computer models say they more or less exactly cancel out. So this is what the experts say would happen if we stopped emissions. The temperature would be constant. Now, that's not a theorem, but it's probably roughly true. I've tried to understand the models, they're quite complicated. But that's why we're asked to get to net zero. Now, if we have to get to net zero, that means there's only a certain amount of CO2 we can emit without the temperature going up above 2 degrees. So there's a budget for that, and I'll come back to that. Of course, there are other greenhouse gases, particularly methane. They have different effects because they go out of the atmosphere. Methane goes out quite rapidly. If you emitted a pulse of methane and a pulse of an equal amount of carbon dioxide, after 100 years, the effect of methane, the pulse of methane would be 30 times as big. And usually people compare methane and carbon dioxide with the effects after 100 years. They say methane has a carbon dioxide equivalent of 30. But that's a bit misleading because on shorter time scales, it's more like 80 times as big. So I personally think we're underestimating the effect of methane, and we should really take it very seriously. Now, how are we doing? These are the emissions of CO2 from burning fossil fuels to produce energy. So you can see from the beginning of the last century, going up slowly, increase after World War II, and then really going up rapidly. This is the industrialization of China and India. A little bit of a drop last year from COVID, but it's predicted that that will more or less be replaced this year. I'll show you some future predictions in a minute. That's from burning fossil fuels. Forestry and changes in land use, if you dig up the land, it emits CO2, add about another, this is the scale here, this is 30 billion tons a year. We're at about 33 at the moment. Add about 6 billion, and then there's a lot of carbon of other greenhouse gases, methane, nitrous oxide, fluorides. And those add a lot here. And I put this plot up because it shows the contribution of Turkey. It's very small. Of course, back here, United Kingdom was one of the big contributors. But by now, the major contributors, China, it's overtaken the United States, followed by the United States and India coming up rapidly. But all of us are responsible in some way. Now, what's going to happen in the future? So this is, here you see, this is the plot here where it was coming up and it's gone down a little bit. Sorry, I've gone one too far. It's gone down a little bit last year. It's predicted to come up again. And if every country fulfills their current policies and they don't break their own rules, it's expected that the carbon dioxide emissions will be about this amount. That's the emissions every year. Still, it's growing in the atmosphere, of course. Now, those countries have said, we'd like to do better. And this orange line is what their wishes are, the targets at each country. Then it'll go down. But it's not enough. If we want to keep the temperature below 2 degrees, we should be on this green line, the light green line. And if we want to keep below 1.5 degrees, we should be on this heavy green line. So there's a big gap between what's needed and what's happening. You see the same thing here. These are the stated policies. That's the same as this line here. These are the pledges. Now, under the agreement reached in Paris in 2015, every country was supposed to say, this is what we promised to do, and these are the promises. You see, these are the promises of the United States, this is the promises of China. You add up all the promises, they get us to here somewhere. But in 2050, we'd like to be down here, so it's not enough. Now, what about from burning fossil fuels for energy? So if I look at where our energy comes from, this is the primary energy. This is the contribution of coal. These are all added here. This is oil, natural gas, coal, nuclear, hydro, wind, solar, biofuels. And you see that the fossil fuels producing most of our energy. This graph is a little bit misleading. It's using a definition used by the International Energy Agency, which says, well, nuclear actually produces heat. So they've put here the amount of heat produced by nuclear, but that heat's turned into electricity. Nuclear produces less electricity than hydro, so that you have to be rather careful with these graphs. Really what you should do is say, if hydro energy came from heat, it would be 2.5 times as much. And the same thing as wind and solar. But even if you go to a better definition, fossil fuels still contributing 84%, and we want to get them to zero. So what's the prospect of getting this to zero? Well, before I look at the prospect of getting this to zero, I'd like to look at the shares of coal, oil, and natural gas in the last, from 1900 up to 2020. So you see, back in 1900, we weren't using much energy in the world, but it was mostly coal. Then we got into an oil age, and now natural gas has caught up. So at the moment, we're in a rather unique era where oil, coal, and gas are contributing just about the same amount. Now, you can see that there have been shifts from coal to oil, now towards natural gas, but they've been very, very slow. This has taken 120 years. Now we've got 50 years in which we'd like to get rid of this and shift entirely to the renewables and other sources down here. Can that be done? This is a projection of BP, their rapid change scenario, and they think that renewables might change like that. That would be completely unprecedented for some change at that speed. And you can see that even in this, that should say rapid, sorry for the misprint, there's still some oil and coal left. So those would have to be offset, because burning them, even if we try to capture the CO2, we can't capture all of it. Those will have to be offset by some negative emissions. So there's a big challenge here. Now I'm going to quantify this challenge very slightly, or try to. This is a little bit complicated, this graph here, but let me try to explain it. It's a little bit out of date too. But this graph, which was made in 2017, said, let's look at the emissions today in purple from generating electricity. And then the authors said, let us assume that no new fossil fuel electricity generation is built, none. from 2017 onwards. It's not true, of course, more has been built. But suppose it had no more had been built. So this is what already existed in 2017. If it went on running the way it has historically, the same percentage, number of hours in the year and so on, until the end of the lifetime of these plants, which is typically 40 years, something like that, these fossil fuel generation would produce 358 billion tons of CO2. If all the industry that emits CO2 already in existence in 2017, no new CO2 emitting industry was built. That was just run to death, to the ground, 162. This is for transport. If you add up all the emissions of things that existed in 2017, unless the owners were prepared to say, we're going to sacrifice our investment and switch them off, the things that already existed in 2017 will produce 658 billion tons of CO2 by the end of their lifetime. But the budget to keep below 1.5 degrees with 50% probability is 580. And if you're really safe, you'd say, I'd like a higher probability than 50%. You can only afford to emit 420. So the committed emissions take us beyond 1.5 degrees and a good step towards 2 degrees. And at the same time, at that date, these are things that were planned. And actually, since then, a lot more has been planned and a lot more has been built. So there's a lot of existing infrastructure will have to be written off. There's huge inertia in the system. It will be very difficult. The other reason that it's going to be very difficult, or one of the other reasons, is because of living standards. So this plot here shows lots of different countries in the world. I'm not sure where Turkey is. It must be one of these dots. And this shows the energy emission per person, energy use per person in certain units. And this is what's called the Human Development Index. Well, the Human Development Index is a measurement of sort of human well-being, if you like. It's a mixture of the amount of money per person, the amount of education, and life expectancy. So the countries in blue at the top here, one is supposed to be bliss. The countries in blue have high standards of living. The countries in red have average quality of life, and the green have a low standard of life. And what you see is that as you go up in the standard of living, people tend to use more energy. That's not surprising at all. So if these countries down here want decent standards of living, it's likely they're going to use more energy. The difficulty is that when you use more energy, you make more CO2. This is the same Human Development Index, but at this time, it's a CO2 per person. So what we need is that all these countries here need to come down to zero, and these countries here, they need to come up to get more energy, get better living standards, but they'd like them to turn over and come into here. That's a really tough ask. And I happened to be giving a talk in India last year, so I put on here what happened in India. From 1990 to 2016, indeed, the amount of energy has gone up, the standard of living has gone up, and the amount of energy has gone up, but the CO2 has gone up also. So it's a really tough call. Okay, so we need to do it. It's difficult to do. How can we do it? Well, there are 3 measures that can help us decarbonize. None of them can really do it on their own. First of all, we can try to reduce the need for energy. How can we do that? We can do it with better planning. Make sure that in every city there is a lot of public transport. There are bicycle lanes. Make it easy for people to walk, to use public transport. People can change their lifestyles. It's being proposed here that people should stop eating meat. I don't know anybody who's, well, actually, I know one person, one of my granddaughters, said she stopped eating meat because she's worried about climate change. I'm afraid I haven't done that. I think we're going to get very little effect from that, but we have to try to do this. We can use energy more efficiently. This is essential, but it won't solve the problem. Actually, we are doing better. If this plot here shows energy use, shows gross national product normalized to 100 in 1990, energy use per and CO2 for the world. If you go back to 1960, from 1960 to 1990, every time the world got 10% richer, it used 10% more energy. If it got 20% richer, it used 20% more energy. But when it did that, it used 20% more CO2. And you can see since 1990, we've started to be able to increase global wealth faster than energy, which is good. But still, CO2 was plotting energy up to this date. These are projections to the future here, but it's beginning to decouple. And in the EU, this is also a projection, but from a slightly different later date. You see, the EU has done quite well. It really has decoupled energy use in purple and carbon dioxide, but still not really enough. These things need to go to zero. Technically, we can do a lot better with energy efficiency, but the problem is if you make energy more efficient, that means using it is cheaper and people use more of it. So if you're a poor person who can't in winter afford to heat your house to the temperature you'd like, if suddenly heating becomes more efficient, if you're a rich person, you will use less energy because you're already heating your house to the temperature you want. But if you're a poor person, you will just turn up the thermostat. You will use the same money, but you'll lose more energy. So that's called the rebound effect. And even more serious is what's called the indirect rebound effect. If energy gets cheaper because we get more efficient, people will have more money in their pockets. They will spend it on things that use energy. That will put up energy use. It's very difficult to say how much. The only thing that really seems to work, and I'm going to show this on the next slide, to reduce energy use is the law, regulation. So this shows the fraction in the world of buildings, transport, industry that's under regulation. And you see something like 30% of the world or 40% is under regulation. So this we have to do. But in addition to that, and I'll show you the evidence in a minute that this does work, we need, and that's the rest of the talk, to move to low carbon systems and sources and negative emissions, because we're probably not going to get to zero. So we're going to have to pull CO2 out of the atmosphere. So this slide is a little bit complicated. Sorry, I skipped one. But I'll try to talk you through it. If you don't follow it, doesn't matter. I don't need it yet later. These are the performance of US passenger vehicles in the United States from 1975 to about 2008. And this shows the efficiency measured in ton miles per gallon. Now, of course, that's not the same as fuel economy. The fuel economy depends how heavy your car is. The fuel economy in miles per gallon, so that, if people, the miles they do is sort of fixed by their lifestyles, that's the thing that matters. And the efficiency was, the fuel economy is regulated in this period. Now, these are plotted on different scales, but the efficiency and the fuel economy were both going up more or less like straight lines. So if I slide the scale, I can make them look on top of each other. So in this period, every year, the manufacturers made the cars more efficient and people put more miles per gallon. But then something happened. What happened was the fuel economy standards stopped going up. They were frozen. What happened? The manufacturers went on making more efficient cars, but they made heavier cars. So the fuel economy stayed the same. Actually, that's on the next slide. You can see at this date, they went on making engines that would work better, just made heavier cars. Those are all those SUVs, and they gave them better acceleration. This is a huge effect. It's reckoned that if the US, because of these fuel economies, has saved something like 80% of the annual oil output of Saudi Arabia. But the point about this is that regulation works. It's the only thing that really reduces energy use. Now, let me come to decarbonizing energy, and particularly what I'll call the stubborn sectors. both sectors which are really, really difficult to decarbonize. So first of all, let's ask how we use energy. So we basically buy energy in three forms. We buy energy to provide heat our homes, to cook, heat water, and industry buys energy to provide heat for industrial processes. We buy energy and industry buys energy for transport. And then we buy electricity, which has a number of different uses. And these are the percentages. Almost half our final energy is in heat. By the way, you can ask, why is it that talks on energy are mostly about electricity with usually a bit of transport thrown in? And the reason is that we know how to decarbonize electricity, and heat is much harder. And we know how to try and decarbonize a lot of transport. Now that's the final energy. That doesn't reflect the original energy, because this electricity is mostly coming from burning fossil fuels, which is, say, 40% efficient. So the energy you need to put in to get this electricity is a lot bigger. So this number needs to be increased. Transport, mostly provided by oil, but oil refining uses up something like 8% of the energy in the oil. So the energy needed to get this oil for transport is more. So both these numbers need to go up, but then you get to more than 100%, so you have to scale it back again. And if you look at the primary energy, it's something like 40% electricity, 35% heat, 25% transport. Now, heat is sort of 50-50 in industrial and space and water heating, but actually the industrial is producing more than 50% of the CO2. I'll come to that later. Now, how are we going to decarbonize industrial heat? Some of the CO2 here is just thrown into the atmosphere. We need to stop that. We can use electricity, we can burn hydrogen. We need to rethink how industry works. Space and water heating and cooling is going to become important as the temperature goes up. Already is very important in many parts of the world. Depends on the location. Some will be electric, some could be biomass, some from geothermal energy, some from burning hydrogen. Transport, light vehicles, probably mostly batteries. Heavy vehicles are harder, maybe burning hydrogen, possibly ammonia. Maybe on the highways, the motorways, we will have electrical pickup lines above the road for heavy vehicles, where they pick up, like trolley buses and trams, they pick up electricity. What about ships? There's a 2016 agreement that says that most ships, that about where we should be in 2050. To reach the 2050 target, which is not a tremendously strong one, by 2030, most new ships will have to have zero emissions. So it's a really tough target. Today, almost no ships have zero emissions. The only example of something crossing the Atlantic in a zero carbon shipping was Greta Thunberg when she went to address the United Nations last year, went in a sailing ship. So that's a big call. Aviation, it's rising the emissions 3% a year, or it was before COVID, and the agreement is to offset it. But we're going to have electric planes, maybe for short distance, biofuels, maybe hydrogen and ammonia. Electricity, we know how to decarbonize, I'll discuss it, but it's going to be a lot of wind and solar, but it's going to have to be accompanied by storage to use the times to account for when the wind and the sun is not, wind is not blowing, the sun's not shining, and when there's too much. And also, if we electrify parts of industry and transport, it's going to be a much bigger challenge. Now, one important point is that in electricity, if my electricity is produced from green sources, it's the same electrons come out of the plug. So it has no effect on my lifestyle. So for consumer behavior, doesn't come into decarbonizing electricity except through the price. But how you move around and how you heat your house, that affects your life. So those are much more people sensitive. And we need to look at all these things, including consumer acceptance and policies, together in a holistic way. Now, let me look instead at where the CO2 comes from. So this is in 2014, but it hasn't changed very much. So by far the biggest individual slice of CO2 is in power generation, and that making electricity. Well, we know how to decarbonize that, but since these other things are going to be decarbonized by being turned into electricity, it's going to make it harder. Here is light road vehicles. We know how to decarbonize that. Here are heavy road vehicles, rails, very little, air and shipping, pretty difficult. And then there are these ones, and then there's heating buildings, that's difficult. And here are the ones in industry, iron and steel, cement, chemicals, and so on. So I'd like to just give a couple of examples here. Well, the first thing in industry is again going to be efficiency. So this is an EU study that says in steel, plastics, aluminium, and cement, the European Union, in whenever year this was done, was producing, it was about 3 years ago, was producing, oh, no, sorry, this is a projection. They said that in 2050, they thought the EU would be producing 530 million tons of CO2 from these sources. By materials recirculation, recycling, they think in principle you could save 178 million tons. Then there's product efficiency. What does that mean? That means if you mill aluminium, for example, if you drill into aluminium, don't just leave the bits on the floor, sweep them up, melt them down, put them back again. So they think you could save another 156. And then circular business models. That means sharing cars, sharing offices. Actually, COVID may have increased the scope for some of this. But the EU thought you could save over half the CO2 emissions from industry just by greater efficiency. Of course, that's theoretically. Actually doing it is going to be much harder, but it really shows the real importance of efficiency. Now, I'll give the example of steel. So how is steel made? Iron ore is mined. That takes energy. It's mostly coming from fossil fuels, so CO2. Then you take iron ore pellets, ferrous oxide, heat them up with coal in a coke plant. The coal turns into carbon monoxide. Carbon monoxide reacts with iron oxide to make CO2, which makes iron, and then later steel. And at the moment, this CO2 is just put into the atmosphere, just let go. So what can you do about this? In principle, you can capture the CO2, but the stream is rather dilute. And in any case, you couldn't capture all of it. So what you need to do, if you want to go down this route, you need to redesign the furnace. That will put up the cost, and you need to capture as much as you can. But there are alternatives. So you could use non-fossil fuels in mining, and instead of mixing carbon monoxide with iron oxide, you can mix hydrogen. Hydrogen plus iron oxide makes iron plus water. You can do that, but it's going to be more expensive, perhaps by 20 or 30%. It's being done, in fact, but like all these things, it's not going to be free. Cement, I think I'll have to skip this slide or I'm going to run out of time. But if we look at CO2, a large amount, and as the developing world develops more and more buildings using cement, it's really difficult. And again, cement is made by heating up limestone, and the carbon dioxide is just let go into the atmosphere at the moment. There are various things you can do. You can try to capture it. You can look for alternatives, but it's going to be hard. I won't go through this slide, just say that according to the Energy Transition Commission, cement decarbonisation is likely to give a significant increase in cement prices and could account for something like 60% of the total cost of decarbonisation in the harder to abate industrial sectors. Now, I've said throughout that electrification is going to have a big role. So let's look now where our electricity comes from and what we can do about it. So today, these are in gigawatt hours. So this is 10,000 gigawatt hours a year coming from coal. The total is something like 25 gigawatt hours today. Natural gas is the next biggest, then hydro, bigger than nuclear, despite the IEA showing nuclear as being more important. Here's wind, solar PV, biofuels, and a few other things. Now, what we would like is that these sources here, these go away, and that these sources here, hydro, nuclear, wind, solar, grow to be as big, in fact, bigger, because the use of energy is going up. So electricity generation is a moving target because we're electrifying industry, we're electrifying transport, we're going to electrify heat. So now let me consider, what are these major sources? Well, one is to say, let's go on burning gas, but capture the carbon and bury it. So let's look at that on the next slide. So yes, it can be done. So there are three ways of doing it. You can burn fossil fuels, capture the carbon dioxide afterwards, pump it away and put it back, let's say, into a disused gas field. But of course, this takes energy, so it reduces the efficiency. So that puts up the cost of energy to begin with. And then you've got to invest in the equipment to do this. You could also do it by gasifying coal. So you remove the CO2 before you start, if you like. That also puts up the cost. Or you can burn carbon dioxide with pure oxygen. You get a very high capture rate like that. But this is going to add something like 30% to the cost of electricity, so it's not going to be popular. And the capture is not perfect, and you're still bringing CO2 in, methane in to burn natural gas, and that leaks, and you have the problem of methane emissions. So this can play a role, but I personally feel we should not be going down this route for making electricity, but we should be going down this route with industry of capturing CO2 in steel and cement, because there are very, very few alternatives. Then we can try with biomass. Now, the thing about biomass is when we grow biological material, it takes CO2 out of the atmosphere. Then if we burn it, it puts it back again. But instead, if we captured it and buried it underground, we could make the whole process carbon negative, and that will be a tremendously good thing to do. So this BECCS, this stands for bioenergy with carbon capture and storage, is carbon negative, provided the biomass is well sourced. If you dig up new bits of virgin land to grow fuels, then the digging up the land reduces CO2 and it undoes the good that this would do. So this can be done, and it's carbon negative, so it's a good thing to do. It's not particularly cheap, similar sort of cost to nuclear energy. And in my country, anyway, the capacity for doing this is somewhat limited because we don't grow enough biomass. But this is a good thing to do. Then we can go down the nuclear route. Now, the trouble with nuclear in Europe and North America, it has a terrible record of cost. So this shows, actually, this is the last 32 nuclear plants in the world. This is the generation cost from those plants when built in Europe and North America, up over around $100 a megawatt hour. And here it is in the rest of the world. That's mostly in China and in Korea. And you see the huge difference here. By the way, one of the troubles, that's partly because labor costs are different, but it's partly because it's been managed very badly. One of the things about nuclear is it takes a very long time to build. So the cost of nuclear, while it's being built, you have to borrow money and you can't repay it until it's working. So the faster you can build it, the better. But the cost is very dependent on the cost of borrowing money. So this graph here is rather nice because the bar here, the horizontal bar, is all for the same cost of money, 7%. And the bars go from the low case of 6% to 9%. So it's put everything on an equal footing. Now, this study that I'm quoting looked at the ways you could try to get what happens in Europe and North America down to this level. And they think that you could get down somewhere near here by just basically planning it better. Turns out that a lot of these plants started building it and without having finalized the design. I mean, really trivial mistakes. So it could get better. The other thing that could help is build a lot of plants that are the same. So there's a lot of enthusiasm for what are called small modular reactors. simple design, multiple units on one site, production learning, standardization, short building schedule. Now, in principle, if you make a big reactor, the power should be cheaper than a small reactor, because when you build a reactor, it's the outside that costs. The core is pretty cheap, but it's the core that produces the amount of power. But in fact, that's not happened in practice. So it's hoped that we could build small modular reactors, they might get down to this cost or lower. But whether that will be true, we'll only know when people have built several small modular reactors. And the difficulty is that around the world, there are plans to build one or two, but we need to build several identical ones before we really know if they're cheaper. But nuclear can certainly play an important role in the future. Now, the last topic is wind and solar, and here is the good news. So this is the cost. This is against time. This is for solar photovoltaic, onshore wind and offshore wind. And these are for utility scale, not for what individuals put on their roof. This is the cost. These data come from IRENA. I think they are this year's publication, well, last year's data anyway. And this is the International Renewable Energy Agency. And this is the range of what they think fossil fuel generation costs. And what you can see is that solar photovoltaic is getting down towards the lower end of the region of fossil fuels. Onshore wind is already at the lower energy, the lower range of the cost of fossil fuels. And offshore wind is not there yet, but it's getting there. And I think by 2050 will be down at the same level as fossil fuels. So this is tremendously good news. But the problem is this is the cost, which is not the same thing as the value. Let's suppose the wind only blows at night. So it produces very cheap electricity. But the value, it's valueless if nobody wants electricity at night. So, and these are not always available. So there's a big issue here of how to deal with the fact that solar and wind output are variable. And that's the last topic I want to discuss before I reach some conclusions. So I'm going to illustrate this with a model of power generation in Germany in 2050. This is a rather old model. It was made in 2015, I think. It's out of date and it's not a sensible model anymore, but it illustrates the problem very nicely. It's out of date because it was pre-net zero, and the authors thought that it would be all right to go on using a lot of coal and natural gas. And we know that we shouldn't be using coal at all, and natural gas should be strictly limited. They also assumed that they could reduce by demand by 25%. And demand for electricity is going up as we electrify cars, we electrify industry, we electrify heating. So this is not a very good model. They also, but nevertheless, it's very instructive. They assume that wind will be 3 times what it was in 2015 and solar twice as much. In fact, it's likely to be very, very much more because demand will be more and because we won't be using coal or much gas. Anyway, with this model, this is January in the winter in 2050. In this out-of-date model, they say this black line shows the electricity demand going up in the day, down at night. Here's the wind generation, here's the solar generation. And what you see is there are times when there's too much. And if we go to higher levels of wind and solar, there will be even more times when there's too much. But there's also times when there's too little. And in these times, when there's essentially no wind and solar, however much wind and solar you build, there's going to be a gap. Now you see exactly the same thing in the summer. There's too much in the middle of the day when the sun's shining. There's not enough at night when the sun's not shining. And there are times when there's essentially nothing. So the big problem with solar, there's times when there's more than enough wind and solar, but however much you install, there's always going to be times when there's not enough. So that means you're going to have to store the excess or do something else if you want to power the world entirely with wind and solar. There's another problem here. If you got to say 80% of our energy coming directly from wind and solar, then storage and everything else only has to produce 20%. So we've got something that's giving 20% of our energy, but occasionally it has to give 100% of the power. So it's a small amount of energy, but a huge amount of power. That means a very low, what's called low load factor. So it's going to be expensive. So high levels of wind and solar will be very cheap, but the rest of the system is going to get expensive. It doesn't matter whether it's storage, whatever it is. But that doesn't matter, because if wind and solar are cheap enough, the average can still be cheap. So what are the solutions to these problems? First of all, you'd like to manage demand so as to try and smooth out this peak to bring down the cost of meeting the peak. So actually managing demand, I'm not going to have time to talk about it, will be very important. The other parts of the solution are storage and a larger grid. So I've got a slide on each, and then I'll try and sum up. So storage, I'm leading a large study of storage at the moment. You need to compare hour by hour the future level of demand and of wind, and in every hour find out how much, whatever level of demand and whatever level of wind and solar you assume, how much excess is there, how much deficit there is. You need to take account of the inefficiencies of storage, and believe it or not, there are many studies of storage, academic studies, which haven't done that, and you need to worry about how fast the stores are charged and discharged. We in our study looked at 37 years of data. That's probably not enough. You can have wind droughts where there are periods of a couple of weeks where across the whole of Europe it's very cold and there's no wind. So you have to add contingency, and also because wind and solar are going to change because of climate change. Nevertheless, we found that we could, in this study, power the UK at an acceptable cost with wind and solar supported by batteries and storing power by turning it into hydrogen. We're able to do that in the UK because we've got a capacity to build a lot of salt caverns. So we're rather lucky in that sense. And then we could add other storage for which there are many options. I haven't looked at the situation in Turkey very carefully, but in Turkey you have an option which we don't. One way of storing energy is to pump water back uphill into dams when there's excess wind and solar, and then when there isn't enough, you let it come down again and make electricity. In the UK, because of the geography, there's a very limited capacity for what's called pumped hydro. So it's not a real big option in the UK. But there's a EU study which has looked at the possibility in Turkey, and it's pretty big. As far as the grids are concerned, big grids are being built. If you built a grid that covered the world, you'd have fixed the problem, but it'd be incredibly expensive. And it fixes the problem in two ways, because it averages over different time zones. So you average out the peak in demand, and it averages over different climates. So you average out the wind and solar. But that's never going to happen, that there'll be a global grid. In China, they have got several voltage lines that are connecting the east and the west. So they're going down this route. In the US, in principle, they could have a grid covering the whole US. They don't. They have 3 separate grids. That would help, but it wouldn't solve the problem. In Europe, we've only got 2 time zones, so it's not going to fix the problem. And we're being rather unambitious. The interconnectors are pretty weak, and there aren't big plans to strengthen them. Okay. I was going to talk about the use of hydrogen. I'm going to skip that because I'm running out of time. I could come back to that if there are questions. So meeting the Paris goals of net zero in the second half of the century were very difficult. Not impossible, but a long way to go and not much time. The problem will be solved when we have acceptable low carbon systems and sources that are cheaper than fossil fuels. And that day is approaching, but we're not completely there yet. And we have a lot of existing infrastructure. How can we force it to happen? We can force it to happen by putting up the cost of fossil fuel energy with a carbon price. That's very, very unpopular. It puts up the price of energy. See what happened last year when the French tried to do it, the big strikes of the Gilets jaunes when they tried to put up tax on fuel. However, there are clever ways of doing this. If we say there's a tax on fuel, but we won't put it to the finance ministry, we'll give it back equally to everybody in the country. That means that the relatively affluent people, who are the people who use a lot of energy, it'll cost them a little bit because their energy cost will go up. But if they're rich, they don't care, they get a little bit back. But the poor people who don't use much energy would benefit. So a rebate would be a very good thing from a social point of view and could make a carbon price acceptable. And then we've got to find ways of, by subsidies and mechanisms to reduce risk and the cost of capital, encouraging investment. Countries should adopt strong targets. I'll give the example of the UK on the next slide, but targets won't solve the problem. There are immediate actions that are clear, but I'll come to those, but we're likely to use negative emissions as well. But success will depend on political will to introduce carbon pricing, reorganize markets, as much as technical developments. On the other hand, the technical developments are happening, so it's conceivable that we'll produce a tipping point. Now, just briefly on the example of the UK. Now, let me look at this graph here. This is millions of tons of coal per year produced in the UK. And at this point in 2016, the UK was using the same amount of coal as in 1816. We've been through the coal era, and the government announced today, the British government, that there will be no more power generation from coal from 2024. So we were the first in, but we're back to more than 100 years, to where we were more than 100 years ago, and we're going to zero. And you can see here the decoupling. You can get rid of emissions without bankrupting yourself. We have a commitment to reach net zero by 2020 of all greenhouse gases, and there's a committee which monitors how we're doing. The committee is pleased with this, of course, but says we are not on track. So even the UK, though we're doing well, we are not on track. It's really difficult. You can make scenarios for the UK that meet the 2050 target, but they rely on heroic assumptions, a lot of extremely efficient carbon capture, negative emissions from bioenergy, increasing woodland. You have to be careful with that. If you grow more trees, that reduces carbon dioxide until the trees start dying. So reforestation or afforestation is a good thing to do, and it buys time, but it doesn't fix the problem in perpetuity. However, when we set the target 13 years ago to meet 80% in my country, the assumptions also looked heroic, and now 80% is looking very possible. So I hope and expect that if we all set targets, it'll trigger the technical developments that will allow the targets to be hit. What do we need to do? Decarbonize electricity as soon as possible, electrify the easy bits of heating, build hydrogen infrastructure to apply carbon capture, reduce emissions in food, aim to make the land and net carbon sink, develop options for greenhouse gas removals, and introduce a high carbon price with what are called border carbon adjustments. I don't have time to discuss that. And of course, get into efficiency and recycling. So what about negative emissions? So as I said, the scenarios that get us to net zero, here is one from Shell. They end up with a certain amount of target emissions in 2050, and still the temperature going up 1.8 degrees, so they don't really get to the 1.5, but they need 11 billion tons of negative emissions. Now, I've just discussed them, the ways you can have negative emissions, and one is to suck CO2 out of the atmosphere. So this hasn't really been done. This is a picture of a plant that would take 1 million tons of CO2 a year out of the atmosphere. But to get this amount, 10 billion, you'd need 10,000 of these plants. Well, I suppose it's imaginable, but it's going to be very difficult. Can we do it? Are we going to reach a tipping point? Here's an example of a past tipping point. This is New York in 1900. Entirely horse and buggies. Not entirely, actually. Here is one primitive car. This is the situation 13 years later. In 2013, cars. Not entirely. Here is one horse and buggy. So this is an example of a very rapid transition. So rapid transitions are possible, but this doesn't need tremendously big infrastructure changes. And more importantly, there was a real motivation. I mean, a car is a lot better than a horse and buggy. You could drive off to see your relatives in the country or go on holiday in a car. You can't at the weekend go more than a few miles in a horse and buggy. So, of course, the people who can afford them bought cars. Now we're talking about moving to electric cars. If anything, that's less convenient because we don't have the charging structure yet. So the message of this is that rapid change is possible, but we need incentives and it needs changes of human behavior. Do I think we can meet future energy needs sustainably? I think we can. Do I think we will? I think we probably will eventually when people really start to suffer from climate change. But I'm and I also optimistic because when I talk to school kids and students, they seem to understand the problem. But I'm rather pessimistic that I don't think we'll reach the target as soon as we should. Thank you very much.
Thank you, Professor Smith. This is really a nice presentation, and I think it gave a lot of idea to many of our listeners. There are a couple of questions. I think at some point in your presentation you mentioned as well. Eventually, it is supposed to be in the hands of the countries. And one listener, Yeşim İnce, was asking if it is possible to solve the energy and consequential climate crisis without substantial degrowth in developed countries and a fundamental change in the current capitalist system.
That's a very, very good question. The Paris Agreement is entirely based on voluntary agreements, as just said, or commitments. And that's a good thing and it's a bad thing. It's a good thing because if it hadn't been voluntary, there wouldn't have been any agreement. So it's better than nothing. But the fact that it's voluntary means it's up to each country. And you can see the big emitters, China and India, and the EU for that matter, they're not doing enough. I showed you what their commitments are. They're not big enough. Now for India, it's a really difficult problem. And for the whole of Southeast Asia and for Africa, of course. I showed the plot of standard of living, Human Development Index and energy and CO2. That's really tough. I think it can be done, but it was not very difficult to do quickly, and it can be done without, it won't be done. India's not going to sacrifice improving living standards. You can't expect them to do that. So it really needs help from the developed world. And in fact, that was another commitment in Paris. The developed countries committed to make funding available to the poorer countries to help them decarbonize, but it hasn't really happened. One of the reasons it hasn't happened is that Trump pulled the United States out of the Paris Agreement. It didn't really matter for the United States because the policy is in the hands of the states, not of the Federation, but it happened. The United States was not giving leadership. I very much hope that the United States, the EU, my own country, will give leadership in giving money to these countries. So I think they can do it without sacrificing their living standards, but I think it's very, very difficult for them to do it by 2050.
Yeah, but I would like to bring another part of this question to your attention. And I think in the heart of this question is there's the degrowth of the developed countries. In other words, do you think developed world will give up from their living standards to help the climate change in the long run?
Well, I think so. I'm rather impressed by what's happening in Europe anyway, where people do, of course, it hasn't yet had a big impact on our living standards. And when last year Macron in France attempted to introduce fuel tax, there was a big demonstration. So we may see a lot of that. But certainly in Germany, there is a very keen wish to decarbonize in the UK. And I think it'll change when people see the effects. I think what's going on in the Western United States, I'm very sorry for the people who are suffering in 50-degree temperatures at the moment, but I think that will change attitudes. And the Midwest in the US has suffered from droughts. So I think as people see the change, they will realize the importance. And but as I said, the other side of this, it's incumbent on us, the people who work on the technical side, to bring down the costs. That's what's going to happen, and that is happening. The decrease in wind and solar cost is really, really encouraging. And I think that's why I'm working on storage at the moment. To benefit from that, we've got to have large-scale storage. And then we can, after all, the model that I'm finding shows that in the UK, if we tried to power the UK entirely with wind and solar and storage, if we then added nuclear, it will put the cost up. So, people accept nuclear. Had nuclear we were the first country actually with commercial nuclear power. So I think it can be done, but it's not going to be very easy. By the way, you probably don't want to add nuclear in the UK you do want to add it, even if it's a cost up, because it would decrease the amount of wind and solar you need, so you could get there faster, but that's another issue.
Okay. One question is about the nuclear energy. Berkay Bayrak is asking, there is an opposition to nuclear energy. Do you think maybe in the entire world, will there be a change that will bring the nuclear energy into the climate crisis problem?
I think the opposition is very different in different parts of the world. And in Germany, there's very strong and irrational objection to nuclear. And if you tell people in Germany, 10 years ago, they were building coal power plants, lignite, in fact, which is by far the most dangerous from air pollution. If you told them that the lignite they were building was killing more people than Chernobyl, the world's worst nuclear accident, they just say, we don't believe you. But that's what the facts say. So I think it's a very difficult subject because people don't understand levels of risk. But let me give you an example. The nuclear industry, of course, has to be very well regulated. And we can look at what happened in Ukraine. It didn't kill many people, but it has put an area out of use. In fact, probably only killed about 50 people, something like that. And you can see the danger there, but that was very, very badly regulated. What happened in Japan at Fukushima, the deaths that occurred at Fukushima, very, very few can be attributed to the nuclear accident, less than 5, something like that. But a lot of people, old people, died because they were relocated. They were told to move, so they overreacted. So we have to be careful not to overreact, but it's difficult for governments not to overreact. So let me just give you an interesting example of the degree of regulation. Most materials, in fact, all materials at some level are radioactive. And among different sorts of rock, granite is particularly radioactive. The US Capitol building is made of granite. If the US Capitol building in Washington was a nuclear facility, it would not be regulated. That doesn't tell you it's dangerous. It tells you that the regulations are incredibly strong. And that's good, but they have to be observed. And what happened was they weren't observed in the Ukraine, and they weren't observed properly in Japan to a certain extent also.
I think those regulations may be more important than the technology itself, because different technologies are being developed, but then the strong regulations are more important. Along with this, there is another question coming from another person. This one is from Burak Yağız Dalgıç. Many countries especially the developed countries, are not investing into renewable energy, the solar or wind, he says. What do you think? How do you make the governments to spend more money on the renewable energy? As you said, it may be intermittent, but with the storage, it can be solved, but there should be some regulations there as well. Not all countries are doing it, partly being done, but not extensively. So that's the question.
Okay, so I'm a little bit surprised by the question, and in fact, it tells me I must go back and look in the data, because globally, wind and solar are increasing pretty rapidly. But it could be there are countries that are not in it. I will go and do some homework to find the answer to that question. But I think that the countries, if they've got sensible technical advice, up to a certain level, you can absorb a lot of solar and wind without needing storage. I mean, you know, you can get very little has to be thrown away. I mean, the problem is, I mean, solar's not there at night, so you don't have to throw away much solar anyway. Wind, you know, okay, we're at the level in the UK, a little bit of wind is thrown away at the moment, but very, very little. So you can get to pretty high, and yet we're at 20% of wind and solar, something like that. I don't remember the figure. So I think it is cheap, and people will go down that route, and it's getting cheaper. Solar in particular is getting cheaper, and there are developments like using perovskites and so on, which can make it even cheaper in the future. The change has been pretty rapid, so that you need to, remember I showed you the graph of how fast the costs have gone down. So you need to allow a certain amount of time for the government to react and to invest.
Okay. Well, then with your discussion, there is one question that you may want to really answer. This is coming from Yasin Toparlar. He says it's very interesting, your talk, but if you will be able to think an alternative to gross domestic product, to GDP of the countries, which will really indicate how good they are working on the sustainability goals. This is Jeffrey Sachs' question, but I'm sure you...
Yes, well, people have tried to produce such measures, but I can't really answer that question because I haven't looked at them carefully. But it's quite true that the GDP is not a good measure. People have tried to make happiness indices of different countries, how content people are, and it's correlated with GDP. I mean, obviously, if you're living in a slum in Mumbai or somewhere, you know, you're less likely to be happy than somebody who's not worried about money. But the correlation is not strong, and I think people need to change their attitudes. And that's why I think this Human Development Index is, it's got money in it, but it's got two other really important things, which is life expectancy and the degree of education.
Okay. Well, then there's one more last question. This will be in line with what you just answered. The developing countries or new developed countries, do you think they will try to remain carbon neutral? Or will there be a change? Will there be a different standard for developing countries versus developed countries?
Well, I mean, first of all, there has been an argument when the global climate change talks began from the developed countries saying, you've all developed and you developed and got rich, United Kingdom, for example, by burning coal and gas.
Yes.
Who are you to tell us not to do it? We ought to be allowed to do what you've done. And
Yes.
that is a good argument. But you need to look at the cumulative emissions. And the UK, if you go back to 1900, of course, the UK had produced something like a quarter of the world's emissions, and the United States a quarter, and Germany a quarter. But now we are vanishing from the picture. I mean, China and India are becoming serious. And what I showed you was actually the actual emissions, not the cumulative emissions, but they're becoming big players. So in a sense, that argument is getting weaker. But it's a good argument, and I think you know, there are going to be some countries, probably Brazil, I mean, India and China have expressed the wish to decarbonize. So that's good. But Brazil has more or less said, none of your business, and we think climate change is nonsense under the present government. So again, these things will really only change when people start to see the effects.
Okay.
And that will happen. And it's been well said that if carbon dioxide was purple, we would see it and probably people would change their behavior, but it isn't. But I mean, another good reason, as I said, is air pollution. And certainly air pollution in China, the changes of policy in China were driven by protests about air pollution before they were driven, or more than they've been driven by protests about climate change, because people were feeling that. I mean, you know, if you go to Beijing, anyone in the audience has been to Beijing knows 10 minutes after you get off the aeroplane, you have a sore throat. And the people who live there object to that. So these secondary effects are activating people. But I think that's a very good question. And that's in a way in part of my answer. I think we can do it. And I think eventually we will do it. But I don't think we're going to do it as soon as we should.
Okay. We covered all the questions, but I will ask you one question for you to answer in 1 minute based on the slide that you skipped. What do you think about the hydrogen energy?
Okay, so hydrogen has been pushed tremendously and over-pushed, in my opinion. I think it's going to have a role in transport. It's probably going to have a role in parts of industry, in just being burned to make industrial heat and to make steel. I think it's going to have a role in energy storage. In this country, there's a big discussion about using it to heat our homes. I personally think that's not necessarily a good idea, but it maybe should happen at some level. You've got to be on the gas grid to use hydrogen and put hydrogen in the grid. And that hydrogen would have to come from natural gas and no leakages there. So I think hydrogen is going to be important, but I think that it's been overhyped. The costs of hydrogen are coming down. We've looked very closely at that in electrolyzers for making green hydrogen with no carbon dioxide. And the costs of turning hydrogen back into power are coming down, which you would need in storage. So I think that hydrogen is going to have a number of important roles, but it's not going to save us from everything, as some people seem to think.
Okay, that's great. Thank you very much, Professor Smith. I think you have a very thorough overview of the problem as well as possible solutions. As you mentioned, it's not easy to get this solution in one way or other. There will be multitudes of solutions, and they should all work together. We really appreciate that you gave us this presentation at the end of this year's schedules. We hope that we will see you sometime in Istanbul. If you were in Istanbul, you would have been presented some certificate. This would have been the poster that we would have given to you, but hopefully you will be here, and at that time we will hand it to you.
Okay, thank you very much.
We thank you for your time and efforts, and looking forward to seeing you in person later.
I'm looking forward
do you have a question or any comment?
Just to say, I'm looking forward to seeing you in Istanbul, and I appreciate the attention and questions from the audience, which show the audience is really paying attention.
Thank you. Ali Hocam.
Thank you. Thank you very much.
Okay. Thank you.
Wonderful. Thank you.
Thank you everybody. Teşekkürler herkese. İyi yazlar dileriz. Dikkatli olun lütfen. Hoşça kalın.